Hello dear professor, it is Resul. Today we will talk about our mechatronic system design final presentation. Advisor and team members are shown. Our project name is a fixed-wing UAV as a mini-air vehicle carrier. In our project, a mini drone will be carried by fixed-wing UAV and released to the operation area. Drones and fixed-wing UAV have strong sides as compared to each other. In our project, we aim to combine those widely used vehicles all around the world. Firstly, drones will be placed before flight. When the fixed wing reaches the operation area, it releases the drone, and the drone stabilizes itself in the air. In our scope, the aim of the drone is descending to the ground.
Hi, it's Selim. In this project, fixed-wing UAV that will be designed according to requirements. The plane will basically fulfill the flight operation manually. Main purpose of designing plane is carrying drones in it, so that aerobatic and instantaneous movements are not specifications of plane design. Other properties are given below. Block diagram of plane is shown with components. At the first flow diagram, system design sequence is shown. At the second diagram, propulsion system diagram is seen. Motor and battery selection are not single-step work. There will be a loop for this process to optimize the weight. Plane wing size table is created and undercambered MH11 for airfoil is selected for main wing due to high lift requirement. NACA 0010 is preferred for tail wings because of symmetrical structure. According to given examples, thrust-weight ratio is selected as 0.5 to 0.7. Maximum weight of the UAV was defined as 3 kg, so that required thrust will be in that interval. According to investigated examples and test results, Sunny Sky brushless DC motor is selected. Maximum RPM value is calculated by motor and battery properties. The obtained values belong to no load speed of motor. Emax ES 3050 for servo motor torque is sufficient for required torque value to rotate elevator. Two different graphs are shown below with comparison of thrust current and efficiency current curves. In first graph, according to motor datasheet, thrust values are investigated. In second graph, efficiency of motor propeller pair is observed with same parameters. As a result, according to needed thrust value, 12-inch diameter, 6-inch pitch propeller, and 4S LiPo battery are chosen. Speed of propeller is calculated approximately 7,700 RPM after losses. According to that value, 1,750 gram thrust can be drawn. As a result, thrust values that found from either motor manufacturer or propeller manufacturer data are had in required thrust interval. Required battery capacity is calculated with respect to 10-minute flight time. For a stable flight, center of gravity should be placed at 30% of short, and nose heavy plane is proper for stability. Also, drone's departure scenarios are investigated. As seen from above, with all entered values at 0° angle of attack, speed of plane is observed as 11.7 meters per second, which is close to the estimated speed. Lift coefficient is 0.78, which is sufficient for 3 kg total weight. Pitching moment coefficient is one of the important parameters, and it's observed almost zero, which is also sufficient. From given equation, required lift value at cruise flight is calculated and checked from graph. Moment graph is proper for flight. It's observed that positive moment at negative angle of attack and negative moment at positive angle of attack. For plane longitudinal stability, it's required. Phugoid mode. An oscillation motion is continued as can as possible by plane. When plane starts to accelerate, lift also increases with double of speed, and plane starts to rise again. At these conditions, angle of attack is constant. Short period mode examines the behavior of plane against the disruptor effect applied from pitch coordinate. After analysis, damping factor is obtained as 0.658, which is sufficient for plane. When plane's lateral direction is disturbed, plane tries to reach its steady position by creating roll angle and behave to reach its steady condition as soon as possible. Finally, final design of the plane is drawn with components.
Hi dear professor, I am Ömer Yahya. I will talk about foldable drone and carrier mechanism design. Drone design properties: 250 gram weight, foldable and self-opening operation, folded dimensions must be less than that dimensions. Block diagram of drone is shown in figure. The useful load volume has been reduced by providing the arms to be foldable with the joint design. An elastic rope design has been made for self-opening in the air. The image shows the drone opened and closed position. It's seen in the technical drawing that the designed drone has reached the desired dimensions, thanks to its folding feature. 46% gain in volume was obtained. Explosion view of the air vehicle is shown in the picture. In order to move an aircraft weighing 250 grams easily, at least 500 grams force thrust is required. The designed drone must be agile to balance in the air and to complete the tasks. Therefore, this motor weighing 7 grams, which can be produced 207 gram force with 3S battery and 2.5-inch propeller, was chosen. Flight time calculation is estimated with 1350 capacity battery and finded 8.75 minutes. Weight and cost estimation is shown in the table. We provide the weight requirement with designed 3D models and selected components. A triple capsule has been designed for easy storage of the designed drone. Circular motion of the servo motor is transformed into linear motion with a gear design that includes a pinion gear. With every 60 degrees of movement of the servo, a drone leaves the aircraft. The cover will move on a rail.
Hi, Resul again. In this project, the attitude control is considered. Since the altitude control is simple, it is designed as PID control. When the quadrotor is falling from the sky, it may experience angular orientation more than 90 degrees, which possibly lead to system crash. Sliding mode controller is applied to overcome that issue. It's a robust controller that provides desired performance in the presence of disturbances or uncertainties like parasitic or unmodeled dynamic. Firstly, let's talk about inputs of the quadrotor. Quadrotor is a 6-degree of freedom system which has only 4 inputs from motors to be controlled. The control inputs from U1 to U4, which corresponds to altitude, roll, pitch and yaw controller input respectively as shown, where omegas are angular speeds, V and D are the thrust and drag coefficients. Sliding mode controller uses a high-speed switching control load to force the state's trajectories to follow a user-defined surface. For roll angle, firstly, we define a surface for the system in terms of roll angle and roll rate. In general, a state and its time derivative. Then Lyapunov function is selected as shown. Based on Lyapunov function, an exponential reaching law is proposed for the controller as follows. Finally, we equate proposed law, reaching law and derivative of selected sliding surface from quadrotor motor. Roll acceleration is obtained and plugged into equation above. Finally, control input for roll angle is calculated as shown. Same method is applied both pitch and yaw controller. Here is the model of real quadrotor of Simulab, which mechanical parameters are calculated. This vehicle is heavier than our design and it's bulky as compared. If we obtain stability with this vehicle, it will be easy to implement with our design. The dynamic model is obtained from literature and implemented through Simulink. Here is the roll angle control structure which controls the roll input from the quadrotor, which we derived before. The surface is obtained through the inputs of the controller. We assume that when the quadrotor is released, its initial position is -3/pi. Desired roll angle is set to 0. As seen in the result, there is no overshoot in the response, and settling time is sufficient enough to stabilize the vehicle in the air. As we talk about, the condition must hold. Otherwise, system may collapse. As shown in the figure at the left, in each time instant, surface and its time derivative multiplication less than 0. We can see that the state approaches 0 at the right side. Here is the sliding surface that we defined when we start our controller design. The system may be driven from any initial state to reach switching manifolds in finite time. In sliding mode phase, the system is forced into sliding motion. Then the system reaches the equilibrium position as shown. Here is the timeline of our project. We are excited about to see our designs in real life. Thank you for listening.